Okay, we're going to do a more advanced MPI example now. It's still a simple problem. It's looking at a diffusion equation that's shown here on this slide, and we're going to both walk through it on slides and through the portal. The diffusion equation is just stepping forward in time the concentration of some quantity phi with the, under the influence of a diffusion operator d2 by dx squared of phi times some kappa, okay? And kappa is a diffusion coefficient, phi is the concentration of some property. I'm going to step forward in time discretely using just a simple Euler forward scheme where we take phi at n plus 1 and add to phi. We calculate it n plus 1 by adding to phi at n, time step times this discrete diffusion operator in space operating on phi n, where the discrete operator in space is just taking the two adjacent grid points and dividing by the grid separation, which is the where I and I plus 1 of the indices of elements holding numerical values on the discrete grid. So this code is all in an IAP GitHub repository I have, and you can go there and look at it at any time. So what we're going to do is actually just look a little bit at the serial code, but then we're really going to focus on how we make the serial code parallel. So the serial code executes for a given initial condition something that is shown in these plots here. So if I give a 100-point Gaussian as the initial condition, that's this plot on the left, then you can see that I had a kind of Gaussian bump, which is this yellow concentration. It's my phi concentration on the y-axis, my grid points on the x-axis. And as I evolve time t forward, the concentration kind of gets diffused out and things wrap around at the edges. So anything that goes out at the right-hand edge here comes in the left-hand edge. Dots here just show the initial condition profile and the discrete points, which I sampled this function for those I and I plus 1 operations, okay? In the parallel form, what I want to do is do the same equation, okay? So this is the numerical solution shown in these plots. What I want to do in the parallel form is do the same equation, each rank. I want to go through each rank and split up the domain so that, let's say if I have 4 ranks, then the first rank is rank 0 is going to take the first 25 points, rank 1 will take 26 to 50, and so on. So I'm going to walk through how we do that, and by looking at the various steps in kind of painful detail of what it involves. So, so how do we transform the notebook, and I'll show the notebook in a second, that does the notebook performs this operation into a Python code with different ranks stepping forward different subsets of the points in parallel and exchanging their neighbor information. So let's start by looking at the notebook so we can log in. We're going to, again, launch a GPU style notebook just to make sure the MPI is compatible with the notebook environment. Wait for it to start up. And once it's started, we'll be able to go into the notebook and look, or into the portal, and look at the notebook. So my notebook is in this directory, IAP 2022, I downloaded from GitHub. And this is the actual notebook. So I open that up. So this is the serial code. So it, as I say, it has some comments describing the same things we saw on the slides. And then it has some arrays that set up discrete points. We've got 101 actual discrete points for the wraparound condition, and then some operator for doing wraparound periodicity, and then some function to calculate the actual x coordinates, and then an initial condition. And with the initial condition, we end up with a Gaussian distribution of over 100 discrete points where the maximum of the Gaussian is in the middle and it has a value of 1, and things wrap around at the edges. And the time stepping is very, very simple for this. Yeah. So simply we take a first derivative, calculate the derivative of the derivative, the second derivative times our diffusion coefficient. We do this kind of wraparound condition even for the serial code because we want to still go from this edge to that edge. And then we step forward in time. We just say that the value at the new time is equal to the value at the old time plus this second derivative times the time step. And this takes a little, it actually records a little movie as well in the serial code, okay? So now what I want to look at though is how do we take that and turn it into a parallel code? And the way we're going to do that is looking at various steps, 6 steps in Python, okay? So to transform the serial notebook into a parallel code, we'll follow a gradual set of steps. These are also in the GitHub repository. You can download them from there. Step 1 sets up MPI in Python. Step 2 communicates between ranks, does a little bit of communication illustration. Step 3 does the sorts of things that you need to do in actual MPI code. That is, you take your discrete domain of maybe 100 points, and you have to actually subdivide it between ranks so that each one knows which bit of the subdomain it's responsible for. Step 4 is a piece where we kind of check each rank has the section that's expected and actually do a little bit of exchanging of information. Step 5 makes some plots of the initial conditions. Oh, sorry. And then step 6 actually does the full time stepping. Okay. So step 1, this is kind of very short and looks much like the hello world example that we saw before. So step 1 is just setting up MPI in Python and writing out rank numbers so that we can see that we know how to do this. So this is the command on SuperCloud that will do this, and we'll just show how to do this in actual practice. So to do this in practice, we're going to do everything in a terminal. We're going to do terminal, and we're going to go into the IAP GitHub repo directory, and I have reminded myself of the commands I need to set up the environment here. So I just need to load the MPI module. I need to set a Slurm environment variable that isn't set in the notebook sense. And then I just listing the modules to check where I am. And then after that, I can do this command for running a Python code now under MPI. And I'm adding in this extra strange no open IB option that is just required because the drivers are not quite the same as how the MPI was built on this machine. So Python, and then if I do step 1.py, so this is how you run a Python program under MPI. You start it with MPI exec, just like a C program, and then you run the Python interpreter and then the program you want to run. So if I do that, I get out these rank messages, and each rank knows its individual rank and knows how many total ranks there are. And I can just see this simple code here. So that's fairly simple. So now we're going to do step 2, which is let's send some information between ranks. So we're going to use the send and receive message options of MPI, where a rank in MPI provides a function to send a message to another rank where you specify what the other rank to send to is, and to receive a message where you specify which rank you want to receive from. So we have some code in step 2 that follows our step 1 code that will actually figure out who's the rank to my left and who's the rank to my right. It will do some wraparound. So if I'm on the leftmost side, it's going to say that my rank, the rank to my left is actually the one on the highest number rank. If I'm on the rightmost side, it's going to say the one to my right is the lowest number rank. And then it's going to send some messages, and we're going to just check that that works as expected by sending messages that say, you know, I've received a message from a particular rank and I send a message to a particular rank. So we can test this in a terminal, actually live, and we can see that we got, you know, I sent hello from rank 0 to rank 3, okay, and then somebody received hello from rank 0. This is rank 3 receiving it from 0, so that's kind of what we expect. Yeah, the ordering is not always guaranteed because it's a parallel program, so the actual IO statements kind of can interleave in strange ways. So you see it received the message before it thought it would, printed it, received the message before it printed it, the other rank printed it, sent the message. The ordering of the actual messages is determined by, you know, who sends when. So then step 3 is moving slightly beyond that, we have to now divide up the domain that we're interested in into subregions that each rank can work on. So this is what this sort of convoluted logic here says, you know, take the domain size, do some modular arithmetic to the total domain size, do some modular arithmetic to figure out how much, which parts go to which ranks, and then write out that information. So here we're writing out that rank 0 has the local section 0 to 2, rank 1 has the section 3 to 5, and so on. So we're doing this with a convoluted just set of 12 points, but we're then checking that those 12 points are evenly distributed over 4 ranks. So I can do that here and just check that that is working live. Here we see at the bottom exactly the same sort of information. Note how the ordering is again not deterministic, so if I and not sequential. So rank 2 wrote out its local section, which is the correct one, from 6 to 8 first, and then rank 0 wrote its section. And if I do it again, we'll see, I'm not sure it'll do the same order. So this time, yeah, the ordering is different. It's 0, 1, 3, 2. And that's a feature of parallel programs often, that, you know, where you don't have something that interdependence between the ranks, the ordering of events can be independent of each other. So now we need a step 4, which assigns a number to each local region of a rank and then shares adjacent regions between ranks. And if you'll see, the array sections that each rank is looking after actually have some padding on the sides for their neighbor information, okay? And so this is what's going on here. Rank 1 is assigning 1, 1, 1 to its kind of points it owns, but then it's also receiving 0, 0 from the rank on its left and 2, 2 from the rank on its right. So this code is, the code to do this is sort of worked out here in Python. It has code to work out who your neighbors are, and then kind of who to send things to and who to receive things from. So if we go and, you know, the slides obviously show fragments of the code, all the steps 1, 2, 3 code precedes this. In the code that's actually in the GitHub repository, then the entire sequence of code is there. So here's running this, here's now getting the same information. So rank 2, for example, has 2, 2, 2 in the points it manages, so it has its own rank in those, and then it has 1 to its left and 3 to its right. We can see that rank 0 has 1 to its right and 3 to its left, reflecting the periodicity that we've set up. And if we just look at the code for this, that's not just the fragment that's on the PowerPoint slides, then it has all this other previous steps preceding it to work out kind of which parts of the arrays go where and what values to write to which sections of the array. So there's a lot here. I'm sort of walking through it fairly fast. If you are thinking about doing problems like this, this is a good way to kind of get familiar with it, and all the code here, you can kind of work through it yourself, try and play around with it and see how it works without in your own time. So now step 5 is just really a step to check that our ranks are correct and our initialization is writing. So here in step 5, what we're actually going to do is carry out our initialization function, and this is phi init, the Gaussian, on the local points for each rank, okay? And so, and the best way we do that in Python is actually we can write out some, so we can write out the numbers, but in Python it's very easy also to write out some pictures. So we're actually going to save some images of the rank. So, and if we go here, we can see now, it should be recently modified. Here we go, we've written out initial conditions for each of rank 0, 1, 2, 3, and we can look at these files just to check they look the way we expect. So in rank 0, we have the first part of our Gaussian going from 0 to only 0.05. And over now we've got, I think, 400 points. So we've got 100 points given here. Okay. And then in rank 1, we have the next section, which is, this is 0.05. Then it goes all the way up to 1. In rank 2, we have the next section, which goes down from 1 back to 0.05. and everything is symmetric, so that by the time we get back to rank 3, it looks like the mirror image of rank 0. So that is shown also in these plots here, just to capture it on the slides. So it sets initial values for each rank. So that actually sets us up then to do the time stepping part. And the interesting thing is in some ways, the time stepping is very similar to the serial code. It's all the setup that you actually have to add for MPI. But if you go to the serial code, and I'll show them side by side in a minute, it's very similar. It has a time stepping loop that goes over a number of iterations, 1 to 500 in this case, calculates some derivatives, updates edges. In this case, there are some interior edges in the, as well as the wraparound points at the end, and then steps forward. And rather than saving figures to the canvas thing in the serial code, we actually write out the images of the ranks as they diffuse into flat PNG files in a directory called fig. Okay, and so what comes out of this then is a bunch of plots at different iterations now as well. So our rank 0 phi variable at iteration 0, at iteration 100, 120, and so on, and then our rank 1 and so on. So we can see all this in the notebook. If we go here, we can run the code. And then if we go into the browser of the portal, we can go into the figs directory, and we can look at any of these. And so if we, they're kind of, the timestamps are so fast that you don't see, they're not quite in order. But if we looked at rank 0 iteration 40, the orange line, I think, is the diffused value. The dotted lines are the initial conditions. So we're spreading out the Gaussian from the higher values that were in rank 1 into rank 0, and over time this end will also lift up a bit. So if we go maybe a bit later in time, let's try and find a rank 0 with iteration, say, 260. We'll see that, yeah, that the Gaussian is sort of smoothing out. The steepness is in the middle is going down. It's rising at the edges till ultimately it'll just be the kind of mean value across the whole thing. That's what diffusion does. And then we can look at other ranks at the same iteration. So we can find rank 1. At iteration 160, what we see is the peak of the Gaussian, which was at 1, has now fallen down to 0.6-ish, and that the kind of shoulder is less steep. It's flattening out, as you might expect with a kind of diffusive process. And this is just showing some snapshots from this on the PowerPoint slide. It's instructive, I think, to just look at the serial notebook time stepping loop in Python and the parallel Python time stepping loop. They're very similar. The plotting was a bit different, but otherwise they're almost identical. And this is because really all the MPI stuff was required in the early setup, and then we kind of overloaded this halo function to allow this communication between the different ranks. And once we've done that, the main time stepping part can actually look very similar to how it looks in the serial case, making it kind of easier to understand sometimes as well. So